There we go. Be over inside. Is it recording? Is it? Well. Is this working? That is what I am wondering. Somebody type in the chat if it is. Is it working? Somebody please tell me. Boo! Whoop! Anybody? No? one who's actually... Wow. Oh. Not many people. How many questions? There's literally the... I'm the... Hi, Andrew. Yeah? Any questions? You know, like, specific question... Anything whatsoever. With ions. How they react and whatnot. Or whatever. You know, there's like a 30-second time delay between what I say and what actually goes up. Might as well just bring all these out. Okay, ionic bonding. So ionic bonding is... Woo. So first we gotta start with ions. So ions are when either a metal loses an electron and becomes positive, and that is then referred to as a cation because it's positive. Yeah, I had to use that reference. Or an anion, meaning when something, meaning it gains electrons, making it negative. And now, let's use let's just skip this. Skipping. Here it is. Okay, so everyone wants to get to a noble gas configuration. For sodium, that configuration is neon. So and the closest neon's the closest noble gas. So it will want to, since it's the closest noble gas, instead of be doing all that work and getting 8 electrons, it will do the simplest thing, just lose one and have the neon configuration, and then it will be positive. Chlorine wants to get to the argon configuration, which is only 1 away. It needs to gain 1. So, sodium being nice gives chlorine a gift. That then makes chlorine like sodium, and they want to bond. In reality, one gets a negative, one gets a positive charge, and opposites attract to cancel each other out. Any other questions? I told you there's a huge time delay. So that's why there's going to be huge spans of no talking. Oh, naming is... gotta skip past all this. Okay. Cations only ever have one charge. So, and since they're positive, and since they're at the start of the periodic table, they will go first. And whenever it's just a ion of that, it's just a simple name. So magnesium. And if it's a transition metal like iron, you have to label the charge of it because it has more than one possible charge. So, and instead of using numbers, you use Roman numerals. So, sulfate, it is sulfur, oxygen, and oxygen. So, sulfate, sulfur. Oxygen just kind of loses itself. So, since chromium can have more than one charge, and it has, we can just use the flip-flop method and just make that a positive 3 and a negative 2. It takes 2 chromiums for every sulfate. So it'd be chromium 3 sulfate. And that's the only example in this PowerPoint. Wow, I may have to just open up. Well, wrong. File. New. Back document. So, take for example, if we have, so we have Na3, which is 3 sodium, and N2. Now, since sodium has a charge of positive 2, and nitrogen has a charge of negative 3, they could actually bond in this format. So, like before, we simply call it sodium, but instead of calling it nitrate refers to a different actual chemical. So, the Roman numeral is based off of, sorry, I just looked down. The Roman numeral is based off of the charge, based off of the charge of the ion that you don't know. And you figure that out by using the information you do know. So, the ion whose charge you do know, which is on the opposite side, which tends to be negative, you figure out the negative charge and the ratio to figure out how many of that molecule it takes to bond with how many of that molecule, and take that charge, the ratio, for example 1 to 1, if it's bonding with something that's negative 3 and it's a 1 to 1 ratio, that means it's going to be a positive 3, so it's going to be whatever that element is, 3. But something more complex, like it's a 1 to 2 ratio. 2 of 2 of whatever has that negative charge. That would mean that whatever it is, it has to have double the charge of, yes I will, double the charge of that other molecule. So no, it's not how many of the elements, it's how much. The Roman numeral is how much of, is what charge that particular material has. So iron 3 would be an iron molecule with a charge of +3. So it could be iron nitride. That would actually. Because Fe can have, I don't know why I remember this, can have a charge of either +2, or +3. And since nitrogen, since nitrogen, we know you use what you do know. So the nitrogen, which we do know, must have a charge of -3. So it would only bond in a 1-to-1 ratio of an iron with a +3. That makes sense? So let's just get rid of that for now. Like I was saying, sodium has a charge of +2, which we do know, and nitrogen has a charge of -3. The only ratio in which they could bond would be a ratio of 3 sodium to 2 nitrogen. Want we just go over the Roman numerals again? Just so you know, there's going to be a very long pause while I'm waiting for you to respond to this answer, because it's a time delay. Oh, you use the Roman numerals when you do not when there is more than one charge. So like you can't, like there's period 1 in which you always know the charge, period 2 which you always know the charge. Well, not period, group 1, group 2. But when you hit group 3, it gets a little iffy because it's a whole different ballgame, and it can have multiple charges. So whenever you can have multiple charges, that you can no longer just place the name down without stating the charge, because it's no longer has an assumed charge. So sodium will I'm pretty sure won't have a charge anything other than +2. Wait, plus. Is it sodium +2 or? Well, yeah. No, sodium would only ever have the charge of +1. Sorry, brain fart. Only ever have the charge of +1. Well, it could. Yes. And again, there's a time delay. And if there's more than one charge, you have to include a Roman numeral. So, lead, you must use a Roman numeral. Iron, you must use a Roman numeral. Cadmium, I don't know how to spell it. Cadmium, you do not have to use a Roman numeral because we know, although it's a transition metal, it only ever has one charge. May we move on? Or any other questions? You add I to the second. You add I to the second ending of a word only if they're, well, actually, pretty much any time that it is a molecule that you know the charge to. So hydrogen chloride. That is because it is in a normal configuration. But if we do something like, oh, I don't know, hydrogen sulfate, that's different because sulfate is not a single element. It's when you have a single element bonding with another single element, not a compound mixing with an element or another compound. Because SO4 is sulfate. Chloride is just is pretty much just posh chlorine. Yes. Yes, I do. Any other questions? Sure. Chapter summary. So, atoms can be converted into catons by losing one electron because they want to get to the argon the noble gas configuration. And since it's easier to lose one electron in their case, they become positively charged. But for anions, which are usually noble gases, noble gases and anything on that side of the periodic table that doesn't have pretty much anything past carbon. So anything past there will usually want to gain an electron rather than lose an electron. So to do the less work possible, it will gain one or more to become a anion, making it slightly negative. And sometimes cations and anions are formed with the same electron. So sodium, like I said earlier, sodium will want to bind with chlorine because chlorine wants an electron. Sodium has an electron that it doesn't want. So sodium will be nice to chlorine, give it its electron, and it will be a win-win situation. And then chlorine will start looking at sodium in an entirely different way. And then they'll bond because opposites attract. And since sodium is now more positive, it will want to bond with the now more negative chlorine. And like I said, ionic compounds are composed of anions and cations by ionic bonds. They're essentially electromagnetically held together, so that's why they conduct electricity when dissolved in water. This is also why they dissolve in water, because they're held together magnetically. So if something that looks even better than their opposite, such as water, because water is a polar molecule, meaning it has one side that's more positive, one side that's more negative. So the sodium, being positive, will want to ditch chlorine and go for the oxygen in the water because the oxygen is more negative. And since chlorine no longer has a partner, it will want to bind with the hydrogen in the water because the hydrogen is positive as well. Positive also because both those hydrogens in water gave their electrons to oxygen. So basically, it splits up the relationship. But when water leaves, when it evaporates, sodium and chlorine will, say sorry to each other and get back together. And the main group elements tend to form ions, in which they have gained or lost the appropriate number of electrons to reach a noble gas configuration, and they are generally crystalline solids with high melting points and high boiling points. Metals lose electrons more easily than nonmetals. As a result, they're usually catons. Non-metals gain electrons more easily than metals. As a result, reactive non-metals usually form anions. And I'm sorry about the clock in the background if you can hear it. An ionic charge can be predicted using the octet rule or just by knowing. So, period 1 usually has a charge of positive 1. Group 1, and group 2 usually has positive 2, and then we skip pretty much all the way to the end, and we hit boron, which has a charge of positive 3, and everything in that group pretty much has a charge of positive 3. Then we have carbon, and its friends. They are kind of flip-floppy. They don't like to form ionic solids. I mean, they will, but they're more likely to form more equal molecules. And anything pretty much anything after carbon will want to be negative. Cations have the same name as their metal, and monatomic anions have the ending "ide." And for metals whose has more than one ion, a Roman numeral equal to the charge is used in the name of the ion. Cation's name is given first, with the charge of the metal ion indicated if necessary, and the anion name is given second. An acid is a substance that yields H+ ions, or positive hydrogen ions, when dissolved in water. A base is a substance that yields OH- ions when dissolved in water. This means when you put an acid in water, it will split up into H+ ions and some other random junk. And a base will become OH- and water. And if these sound familiar, that's because essentially when you split water into these two, you get, when you split water, like if you take a hydrogen off of water, it will be positive, and what's left will be negative. So essentially, we have a water molecule that is not happy. That's why it's acidic or basic, making it dangerous to the human body and other living organisms. And here are some keywords. If there are no more questions, I will end the video at 9:05. Unless you have a question. Oh, sure. So, let's move back to that. I kind of... Oh, sure, it's a delay. I'm sorry. Okay, so some atoms have properties that change predictability on the periodic table. The size and how readily they'll lose electrons and how readily they'll gain electrons. All these properties depend on two factors. In order of property, the shell that has the outermost valence electrons are in, the greater the average distance from the nucleus there are. That means the less tightly the electrons are held by the nucleus. Using Mrs. Palmer's analogy, Slingshot, you don't even take Chem. Why are you here? Never mind. Using Mrs. Palmer's analogy, helium, which only has 2 electrons, will be able to hold those electrons very close to the nucleus, and is very hard to get rid of that. Take one of those electrons. So, but an element like francium, which is one of the most explosive elements there is, has so many electrons, and they are so weakly attracted to the center that it makes itself fat, and it will hold all these electrons, but it will barely hold them, giving it making it easy for it to lose an electron, and again making it a very fat molecule. Francium, you need to lose some weight. In this case, electrons. Wait, don't lose electrons, you'll cause an explosion. How many protons there are? Only look at this if the electrons are in the same shell. The more protons, the more tightly the electrons are attracted to the nucleus. It's like, yeah, I already used that analogy, so. So, as you go down a group, and this is for the attraction of valence electrons, the electrons are less strongly attracted to the nucleus because each row down is a larger shell, meaning, like she said, being at a movie theater that doesn't have theater seats. If people are sitting in front of you, you can't see because they're in your way, meaning you can't see the movie, meaning you're not very attracted to the movie. So the electrons closer to the center have a great view of the nucleus, meaning they're very close. But the further out you go, the less attracted it is to the nucleus. As you go across a period, they start to lose some weight. So this is because they have a more positive charge and less of that theater effect where you can't see because there's somebody in front of you. Because the positive will attract all these electrons equally. So the upper right hand elements have the greatest attraction. So, like I said, helium is the smallest, most densely packed molecule there is. And francium is pretty much a very ill-tempered fat guy. He's big and very easily triggered. The atomic radius is the distance from the nucleus to the outer edge of the outermost orbital. Like I said, francium, very big size pants. Oh, and ionization energy is the energy it takes to lose an electron, meaning noble gases, very hard to, but is possible. Electron affinity is how easy it is to gain an electron, meaning the noble gases, no, we don't want an electron. So it's almost impossible for them. This also means how reactive they are. The halogens have the highest electron affinity. So they're extremely reactive. And the alkali metals have a very high ionization energy, again, making them very reactive. Kind of like if you put two people in a room who are very easily triggered together, something bad's gonna happen. Slingshot, I'm doing this to help other people study. That's why. And here's a chart if you didn't already understand. Also, it gives me more editing time for gaming videos. No problem. Okay, guys, have a good night.